Welcome to Chemistry's Refrigerator, and that's the icebox. When we're solving equilibrium problems, one of the things that I'd suggest you use for every single equilibrium problem is an ice table or an icebox. In an icebox, what you're going to do is you're going to have a space to organize your information in a very specific way. You're going to look at where you're at now, because if you're not at equilibrium, then you will be approaching equilibrium and your concentrations and amounts are going to change, and they're going to change in very specific ways tied to the stoichiometry. So really what we're doing is looking at a way to organize information. And in most cases, we're going to need it to help solve the problem. And even if it doesn't have to be done to solve the problem, it will always help you see what it is you're going to do in the problem. So I'd recommend you set this up for any reaction that we look at. Now, when you set up an icebox, typically I tend to be a little lazy / efficient, and I've got my equation. I don't really make a table. I just write my equation, then to the left of it I make an I, a C, and an E, and I just use the chemicals in the reaction itself as my headings for the different columns. Now the first row of the icebox table is I, and that stands for the initial amounts. Now usually this is going to be molar concentrations. So typically in a problem where we're dealing with aqueous solutions, gas systems, much of the time we're going to be dealing with concentrations in molarity. So that's what you usually use, but it does actually work for other situations as well. So here's a typical problem. An empty 1 liter container is filled with 1.5 moles of H2 and 1.0 moles of I2. Now in this particular case, we've got moles of particles, but it's a 1 liter container, so moles divided by liters would equal molarity, so it's also 1.5 molar and 1.0 molar. And then a really important idea, because they're going to be using this a lot, is if we're putting things into an empty container, we're not putting in all the chemicals in the equilibrium system. We're typically only putting in some of them. And usually you'll notice most of the time we're adding all the reactants we need or all the products we need. And the other side is usually going to be a 0. So it was an empty container and we just added H2 and I2, so we have no HI at the very beginning. Now technically this is molarity, but you can actually do this with moles because moles are a valid way of counting particles, and in chemical reactions we're looking at how particles interact with each other through stoichiometry. And then for gas systems, we can also look at it from a pressure point of view, because pressure is a measure of concentration, so to speak. So it's interchangeable with concentrations and pressures. And then sometimes you'll end up in moles and they don't tell you the volume. You can also leave it in moles. But usually we're going to go to molarity, and if it's a gas system, we'll sometimes be using atmospheres. Now, one of the things that you're going to do is, once you set up your initial conditions that they're talking about, sometimes they give you other information. Don't forget to put them in your icebox table. Like if they're telling you very specifically an equilibrium concentration for H2 or I2 or HI, put it right in the table where it goes. So if they tell us that at equilibrium the HI concentration is 1.3 molar, oops, I got to jump back. For some reason that didn't write appropriately. Then when I go to set up my problem, it's really critical that I know that whatever is happening with my initial and my change, I'm going to end up at 1.3. And you'll see why when we get into C and E, why that's really critical. So remember, once you've set up your initial, if there's any other information they give you, like a specific equilibrium concentration, put it in the table. Or if they tell you how much something changed, because they could literally say on the way to equilibrium, the H2 concentration drops by 0.3 molar. So make sure any other information they give you at the start of the problem goes in your icebox. But typically you're going to have blanks for C's and E's after your initial step. Now, the next one is the change in amounts, and this is really tied to stoichiometry. Now, you could have actual values they're giving you. So like I said a second ago, it could say it goes down by 0.3 molar. But if you don't know, then we're going to use X's for our values. And one of the important things to make sure is when you put in a number or a X, that you put the correct sign. If it is being used up, it's going to be a negative. If it's being created, it's going to be a positive. And don't just think reactants and products, because these are reversible reactions. They can go to either direction. So it really comes down to in which direction are they moving to get to equilibrium. Are we favoring the production of products? Then our reactants are going to be a negative X and our products would be a positive X. If it's favoring the production of reactants, then our reactants are going to be positive X's and our products would be negative X's. And remember, the number of X's when we're establishing our relationships is purely based on the stoichiometry. So let's say the problem says our container that had 1.50 molar and 1.0 molar I2 put into an empty flask is allowed to reach equilibrium. Well, at that point, we've got to look at what's happening to our amounts and use the stoichiometry to figure out what's going on. So to reach equilibrium, it's going to favor the formations of products or reactants, like I said a minute ago, and that's going to determine your sign. So you really need to think about which way am I moving to achieve equilibrium, making more products or making more reactants. In most problems, what you're typically going to be doing, and this is the vast majority of the time, you're going to have a zero for one of the amounts on one of the sides or for an entire side typically. That means in order to reach equilibrium, you're going to have to produce that. So think of it as you're always going to shift towards a zero. In this case, that's on the product side. So I know in reaching equilibrium, I'm going to use up reactants and I'm going to make products. Now, I don't know how much I'm going to use up on my way to equilibrium. So here's where we're going to use an X value. So I'm going to say H2 goes down by X. Now, based on the stoichiometry, it's a one-to-one stoichiometry between hydrogen and iodine. That means it's also going to go down by X in our I2 on our way to equilibrium because they're the same stoichiometry, they're going down the same amount. And that's also what we're going to use on the product side because if each of those are going down by X and we've got a 2 in front of HI, that means the product HI is going to be going up by 2X. So typically when you're doing a change, that's what you're going to be putting in as some X's with positive and negative values and appropriate coefficients based upon the stoichiometry. Now, it is possible they tell you a change, and that would actually give us what X is, and then we could use that to quickly solve our equilibrium concentrations, which is what comes next. But in most cases, it's going to be like this. They didn't tell me anything about how much it changes. I just know that's the relationship between the reactants and products and their changes. Now, when you go to equilibrium, all you're really going to do is add I and C. So I plus C is going to equal E, our equilibrium concentrations. So if you just add down, you'll end up with 1.5 minus X is going to be our concentration at equilibrium for hydrogen. 1.0 minus X would be our equilibrium concentration for iodine. And 2X would be our equilibrium concentration for HI. So at this point, if we could solve for X, we could actually figure out what our concentrations are at equilibrium. And here is where if they told us that we made 1.3 molar HI at equilibrium, I could use that to solve for X. I could use that to figure out all my equilibrium concentrations. Now, if you're given that concentration, then you're just going to use that to solve for X. So if they told us the H2 was 1.0, so let's look at a different real situation. That means I know that it went down by 0.5, so that means HI went down by 0.5, which means HI is going up by twice that. So this would be an example of how we could establish equilibrium concentrations if they give us any of the amounts. Now the key is we had to establish what it was with respect to X at equilibrium. And then we could translate that into what is the value for X and figure out all the rest. And that's something you do quite often. If they're asking you to find the equilibrium constant K, is you need to know your equilibrium concentrations and then plug those into the equilibrium expression. Now let's look at another situation here. So let's say we've got a situation where we've got this gas system, and notice now instead of concentrations, we're in atmosphere. So what they're telling us is initially we have 3.0 atmospheres of C, and we have no A and B. So we basically put this much in a sealed container, and this is our initial conditions. And on our way to equilibrium, because my zeros are on the reactant side, my products are going to go down. And it's a one-to-one stoichiometry. So exactly how much my C goes down is how much my A and B are going to go up. And then to get our equilibrium amounts, you just add down I plus C equals E. And those would be our equilibrium pressures in this case. It works the exact same way as concentrations. It's just now we're talking about pressures. And you'll see this in gas systems. If it's not a gas system, you'd never run into this kind of situation. But there's one very specific thing that can happen with gas systems. So let's say they tell us that at equilibrium, the pressure on the container is found to be 5.0 atmospheres. What do you do with that if this is our given information? Well, remember Dalton's law. The sum of the individual pressures has to equal the total pressures, and I know at equilibrium what my individual pressures are with respect to x. So literally, just solve for x. In this case, x has to be 2.0, and now I can go in and figure out what my A pressure is, what my B pressure is, and what my C pressure is. So this is an example of a way in very specific gas situations that you end up solving for the equilibrium concentrations. But remember, this only works for gas systems, and it's really an application of Dalton's law of partial pressures. Now, to sum up what we just did, when you go to set up an ice box, you're going to fill in your initial amounts. That's given in the problem, and usually it's going to be molarity, but it could be moles or atmospheres. Then next, you're going to use the stoichiometry to determine how much they change in terms of x. And if the products were formed in approaching equilibrium, that means our reactants are going down and my products are going up, and that establishes the appropriate signs. So most of the time what we're really doing here is looking at where a zero is, and we're going to move towards the production of that, whether it's reactant or a product. And then once we've got our C filled out, now we're ready to add them together and get our equilibrium concentrations in terms of X. Now, what do we end up using this for? Well, usually what we end up doing is we're finding equilibrium concentrations so we can calculate the equilibrium constant K. In order to do that, we need to write the general equilibrium expression. One of the things you'll notice is every single time we do an equilibrium problem, you write the equilibrium expression, which means you have to write the K, EQ, KC, KP, whatever it happens to be, the K equals blank, and then write out the expression with, not numbers, with the actual substances put in. Now there's two general types of problems once we've got that. So we've got our ice box, we have our equilibrium expression written out, and if you don't write it, you're not keeping a 5 on the homework. Then we're probably going one of two ways. If they give us the K or if they're asking us to find for K, those are kind of our two situations. Well, if we're solving for K, then you're going to use the information in the problem to find the values for E, and that can be done in a number of different ways, but once we've set up Icebox and we look at what they've given us, we should be able to do that. And once we've got all of our values for E, not in terms of X, but in terms of actual numbers, we can then plug into the equilibrium expression and find our K value. Now the other situation is when they give us K. And this can get just a little bit more complex, and that's because we're going to get an equation with a bunch of X's in it, and you have to work through the algebra. Nothing that's beyond your ability, nothing that you haven't practiced quite a bit in math class, but you will have to sometimes FOIL things out. So solving for equilibrium concentrations, what you're going to do then is you're going to write your equilibrium expression, you're going to substitute in K because it's given, we know what that is, and then where each substance is, you're going to put in their concentration or pressure in terms of X. And if you look at your equation, you're going to have one unknown, and that's going to be X, and we can solve for X that way. Now, one of the things you might run into is you might end up with a quadratic equation. It will happen. It's not going to happen very much in this chapter, so we'll probably just do it once or twice, and that's it. But in future chapters, it does happen, and we'll look at a way to avoid it when we get there and when we need that. But at this point, if you go to the quadratic equation, you're going to be stuck using the quadratic equation unless there was a shortcut that you missed. And it's just easier to show you the shortcut I'm talking about. So let's say this was my equilibrium problem, and they're asking for my equilibrium concentrations. And that's my icebox. They tell me the K value is 9.0. And this is what I mean by substitute in for the K, the given value, and for the concentrations with respect to X. Now, if you take a look at what we've got, what we have in essence is 2x quantity squared over 2 minus x quantity squared. There is a very specific shortcut you can use to avoid the quadratic here, and at all costs, you want to avoid the quadratic, and that is square rooting the squares. So on the left side, if I square root the left, I'm going to end up with 2x over 2 minus x. And to maintain the equality, I'm going to have to square root the right side. So I picked a nice easy number here so we can do it in our head. That means 2x over 2 minus x is going to equal 3.0. Solve for x, it ends up being 1.2. So now I could go back in and calculate any of the equilibrium concentrations they asked for. In this case, it was AB. So 2 times 1.2 is 2.4 molar. So if you end up with a quadratic, look closely at your equilibrium expression in terms of x and see if there's a square root the squares shortcut that you can apply. And that is a quick look at Icebox in a little bit more detail.